This is a video recording for the second part of topic 5.5, indefinite integral and the substitution rule. Earlier on, we have discussed the theorem 5, the substitution rule, and discussed already example 3. And I'm continue to discuss the rest of the example in the lecture notes for this subtopic. That is to apply the substitution rule to perform calculations of this sort. Of course, all the workings are expressed here, but I am going to go through the workings or steps for this integration. So what we are looking here is an integrations of the form x squared sine of x cubed dx. And to perform the integrations for this type of integration is to use the substitution rule. So you look at it, you try to convert this into the form of f of u du, where f of u is a composite function of u. So the trick here is to be able to find the right substitution for the function u. And it is quite obvious that the choice for the substitutions of u is x cubed. So here we are going to choose the x cubed as the function of u, so that you can perform the differential that will give you 3x squared dx. Okay, so the differential du is just 3x squared dx. So you look at this, you can see then x squared dx is just the du with a factor of 3, so that you can now write this as integrations to make things clearer as x cubed x squared dx, and you multiply by a factor of 3, then you divide it by a factor of 3. Then you rewrite it again as sine of u, then this is nothing but just your du. So this will be actually now in the form of f of u du. So this could be then be integrated in the variable of u, right? So in this case, the u become an independent variable. Then this would be just an integrations of minus cos of u plus the constant. Okay, so the antiderivative to sine of u is minus cos of u. So that is the solutions to the integration, which is quite straightforward. Cos of u, where u is just x cubed plus the constant. So that solves the simple relationships of this. So let me take a look at it more carefully. So there should be a minus sign of sine. So I think there is something wrong here. Yeah, no, there is this thing that should have a minus sign here. So I have to make the corrections to the notes. Okay, so that is a very simple demonstrations of the use of this substitution rule. So let us look at another substitution rule in example 5. Example 5 is the integration of 1 over cos squared dx. Example 5, integrations of dx cos square x dx. So this is just an integrations of secant. Okay, so here I would like to write this as secant square to x, because secant is just equals to 1 over cos. So here we have secant square x to x. Then you have to be careful and be able to choose a very simple substitution. So what we are looking for is the antiderivative of an secant. If the question is the secant x dx, do you know what is the antiderivative to secant square x? I think d dx of tangent x is secant square x, according to my memory. Okay, so let's check if this is true. D dx of tangent x is secant square x. You can always ask Mathematica or your um, check your integral table. So d dx of tangent x is secant square x. So this is true. D dx of secant square x is tangent x. Therefore, integrations of secant square x is just tangent x plus a constant. However, what we have here is not secant square x, but secant 2x, secant square 2x. So you have to somehow take care of this x correctly. So here again, you need to perform a substitution rule. So you have to then try to find a substitution and try to cast the integrations into the form of fu du. I'm going to cast this into the form of f of u du. Here, I'm going to substitute u as 2x. Du equals to 2 dx. Here, dx is equals to half of du. So I'm going to try to write this into the form of dx over 2, so that this gives me du a factor of 2. Then I have a secant square of u. Okay, and here dx over 2 is just du. So by doing this very simple substitution, I have now been able to cast the integrations into the form of integrating with respect to only u, so that this will give me a factor of 2, and this will just give me a tangent square, sorry, this is a tangent of u plus n constant. Okay, so that will give me 2 tangent of u, which is 2x plus n constants of c prime, where here c prime is just 2 times c. So that solves a simple integrations of 1 over cos square x. The trick here is to realize that the antiderivative to secant square x is tangent x. So you have to have this knowledge, or else you will find it very difficult to perform the integration. You have to then refer to the tables of integration to obtain this result if you cannot remember it. But that would cost you a lot of time and effort. But if you can remember these results, then you can perform the integration straightforwardly. So that is the example of 5, which is quite straightforward. Let us look at example 6. Its integrations in the form of 2z over the cube root of z squared plus 1. So this is example of integration 2z dz, and then divided by the cube root. This is a cube root of a factor z squared plus 1. Z squared plus 1. So before I do anything, I would always try to express the expression of a cube root in the bottom to be in the form of some function raised to some index. So I would then write this as say 2z, and then this is to be written as z squared plus 1 raised to the power of cube root with a negative sign. Okay, and then you have dz. So what I have done here is nothing but just re-express 1 over cube root of z squared plus the form of z squared plus 1 raised to the power of minus 1/3. Okay, this is referring to 1 over cube root of z squared plus 1. So now the next step is to find a proper substitution. The proper substitution that you can see here is that here you have z squared and then you have a 2z. So obviously z squared, when you differentiate it, you get a factor of 2z. So to me, the direct substitutions, I mean the right substitution of u is then just z squared plus 1. So you will substitute this factor using u, so that when you differentiate and obtain the differential of u, you bring down the factor of 2z dz, so that this 2z will coincide with the factor of 2z here, and you have dz, which is here. Now you can then cast this cube root with a minus sign, well, this 1 over cube root, into the form of f of u. So here I have this expression of du, where du is just dz 2z. So d2z dz is just a du. Then what is this? This is just the factor of u, right? Here you have a u, then you have a factor of 1/3 minus 1/3. Now this will be in the form of the integrations u power n du, right? So then you can write down the solution to this quite easily to be u power of n plus 1 over n plus 1 plus a constant. So here your n is minus 1, therefore you get 1 minus 1/3, which is 2 over 2/3 plus a constant, and you have sorry, not 2/3, 3/3 here, and then you have u, which is z squared plus 1, and you have a constant c. So I think that is the result of this 2/3 z squared plus 1 plus a constant c. So you always try not to forget the constant c, because if you forget it, then you'll be like crying like a cat. Right? This is what people do when they left the c constants at the end of the indefinite integral. Okay, so the next example would be integrations of sine square x and cos square x. So what we would do here is to try to perform the integration of sine square x or cos square x using the substitution rule. Okay, so let us look at this very simple example. Now, integrations of sine square x or cos square x appears very often. Okay, either integrating sine square x or integrating cos square x are one of the most common integration you will find in the exercise of calculus. So to perform this integration, there are many ways to perform the integrations. The one of the way is to use a substitution rule. So what type of substitution rule should you use in this case? The first step is to not to actually find a good substitution for this, but instead what you have to do is to try to reduce the integrations, reduce the power of the integration. So somehow you need to convert the square function, sine square function, into a function that is linear. So for example, convert into a function that is linear in cos of 2x. So can you try to see the difference between these two? The left-hand side is a function of sine raised to a power of 2, whereas this is just a cos function, linear in x, and is raised only to the power of 1. So any integration of higher power, if you reduce to integrations of a lower power function, you usually reduce the complexity. So the first thing you have to do is to apply the trigonometric rule to simplify sine square into a linear function of cos of sine. And the obvious identity to use is using the cos of 2x as 2 sine square x minus 1. Okay, I think that is the correct identity that relates the sine square and cos x. So instead of integrating sine square x, what you do is that you integrate cos square x by expressing sine square x as 1 plus cos 2x over 2. So you have a factor of 2, just 1 plus cos 2x. Okay, so that is just a simplification using the identity. So here we have not really make any substitution for the integrations of sine square, but instead we are just convert the sine square into a linear function of cos of 2x. And this integration is obviously much easier to integrate as compared to sine square x. So then you can continue to integrate it term by term. The integrations of 1 will give you x. Then you have a factor of 2 outside. So that is the result of the integration for this term. Then you have the integration of this term. So let me write down the integrations. So now what you are left with integrations of cos 2x dx. And here we have actually seen before, I think earlier on we have done at least similar integration. You will substitute u as 2x so that du is equal to 2 dx. Then you simply simplify the integrations of cos 2x into the integrations of the form of cos u. Then here dx is just equals to half of du. So here dx together with this factor of half, no, the dx here have to be expressed as du over half. So maybe I just express the dx as du over half. Okay, that is what is required. Once I have done that, then I'll proceed with my calculations. Then I'll get half. So that as a factor of half du combined with this, then I'll get a factor of 1/4. Then I have an integration of cos u du. And that is almost there. We have then 1/4. And the indefinite integrations of cos of u is sine of u without any minus sign with n constant c. Okay, so that sine u plus c is the antiderivative of cos of u. Then I'll write down the rest. It will be complete. Then it will half of x plus 1/4 sine of u, and u is just my 2x. And you have a constant at the back. So this is the solutions that I obtained. So the solution to the sine square is half of x minus 1/4 of sine square x, which is the answer I am writing down here. Something is not right. I think there's a factor of minus that is different from my solution. So let me see if I have made any mistakes in my sign. So I'm saying that this is cos 2x equals to 2 sine x minus 1. And then I am writing down it. So I'm using this identity so that sine square x is equals to 1 plus cos 2x. But in my slides here, I have a minus sign. So I'm not sure which one is correct. Maybe, so here I'm making use of the fact that sine square x is equals to half of 1 minus cos square x. So either this one is correct or this one is correct. So I think I might be making some mistake here. Let me see what would happen. Yeah, maybe this is not correct. How do I check cos 2x is equal to 2 sine square x minus 1 or the other way around? The way to check this is this. So I'm demonstrating how to check the formula, okay? That is, you set x equals to 0. When you set x equals to 0, you have cos of 0. On the left-hand side, it must be equals to 1. So here it must be equals to 1 when x is equals to 0. So when x is equals to 0, sine 0 will be 0. Then the right hand side become minus 1. So left hand side is 0. Right hand side is minus 1 when x equals to 0. That shows that this formula is not right. Okay, so I have made a stupid mistake. So that should be not the correct formula. It should be equals to cos 2x should be equals to 1 minus 2 sine square x instead of this formula that is wrong. So all the formula that I obtained would be different by a sign of difference. So anyway, we have to correct my wrong calculations. That should be a plus sign and a minus sign. So that sine square x would then be equals to 1 minus, okay, that should be a minus sign here. 1 minus over 2. Yeah, it should be 1 minus cos 2x. So the sine square x would then be 1 minus cos square x. So that is the correction I have to make. So here it would be 1 minus instead of 1 plus. So that should be 1 minus. So here I have a factor of minus instead of plus. Then I'll continue the corrections. Then there should be a factor of minus. Then there should be a factor of minus here as well. Minus sign. Then you have a minus sign. So that would appear to tally with the result that is displayed here. Okay, so I have just shown you how to perform the substitutions of u equals to 2x applied to the integrations of sine square x. The conclusion is that the integration of sine square x has to be proceeded into 2 steps. The first step is to use the identity, trigonometric identity, to convert sine square into cos x using the correct identity. After that, the integrations in the sine square x become easier in terms of the integration involving only cos 2x. The second step is just to use a simple substitution relationship of u equals to 2x to proceed with the calculation. So that is the very simple integrations of sine square x. You can try to use the same tricks to perform integrations involving cos square x, where you convert the cos square x into the form that involves only cos 2x. The calculation for integrating cos square x is very, very similar to the integrations of sine square x, except that you have a minus sign. So try to do this yourself. That's all for this part of the lecture. Okay, so the conclusion for this lecture is that we have learned 2 simple tricks to perform definite integration. The first is the formula that is shown here, the power rule of an integration. Then we also learned the substitution rule, and we have shown a few examples how to make use of these 2 rules to help you to calculate the definite integrals.